Hello everyone, welcome to our Applied Math seminar. So today, Kenneth Allen, he will give us talk about his recent work for simulating runaway electron dynamics. Kenneth is a student of Dr. Lai, and this project is related to Oak Ridge National Lab. I will pass all the time to him. Kenneth, go ahead.
Thank you. Yes, so this is on simulating runaway electron dynamics. So if you saw my talk in the mock AMS, this is going to be similar to that talk. So I'll start with an outline. So the motivation of this problem is for fusion energy. So the Fokker-Planck equation is important for understanding fusion if we want to get fusion energy to work in practice. And then I'm going to talk about this sparse grid DG method for discretizing spatial differential operators. And then I'm going to talk about the time advanced methods for essentially discretizing the time domain. And then I'm going to talk about the Fokker-Planck equation itself. So start with the motivation for fusion energy. So first, what is nuclear fusion? So nuclear fusion is when two lighter atomic nuclei combine together and they release energy. And a heavier nuclei. So for example, the sun is a natural nuclear fusion reactor. So that is how the sun produces energy, is with nuclear fusion. So here's a picture. We have a deuterium and a tritium, and they combine together and they form helium and a neutron, and also release energy. So this is a basic example of a nuclear fusion. So why do we want to use nuclear fusion for energy? So first of all, it's clean, so there's no greenhouse gases, and there's little to no nuclear waste. It's safe, so there's no like sort of potential for a chain reaction with the as opposed to with like nuclear fission, which is how nuclear energy is currently produced. Nuclear fusion is different, and it's much safer. And there's a virtually limitless fuel available. So, such as we could use seawater for fuel, and the cost is very low. So the only con is that we can't. We haven't quite gotten to the point where we get more energy out of nuclear fusion than we put in. So there's still work to be done in order to get this nuclear fusion to work in practice. So here is an example of a nuclear fusion reactor. So this is they call it, say, a tokamak. So it's a sort of torus-shaped device, and it uses a magnetic field to contain hot plasma. And so far, it's a leading candidate for a practical fusion reactor. So it's very, as you can see here, there's some statistics. It's very heavy, 23,000 tons. The heat of the plasma inside can get up to 150 million degrees Celsius, which is 10 times the heat of the core of the sun. And it's also very expensive. It costs, this device at ITER costs $20 billion, more than $20 billion. So it's very expensive. And what we need to do is we need to run simulations in order to understand how the dynamics of this hot plasma that's contained in this tokamak device actually behave. So there's multiple challenges in actually simulating this hot plasma, and that it depends on small features of up to from small time to large time, from 10 to the negative 11 seconds to 10 to the negative, or 10 to the 2 seconds, and between, we need to describe details between, on scales between 10 to the negative 5 meters and 10 squared meters. And the dimensionality of the equation that defines these is this hot plasma. It can be up to 6 dimensions. So it's this sort of curse of dimensionality means that the higher the dimension, we need exponentially more partitions in order to understand. It takes exponentially more time in order to actually compute this the details. And so 6 dimensions is already very large. And the geometry is also very complicated. For example, this in this tokamak device, these sort of boundary conditions is this torus shape. So this is a sort of complicated shape for to understand this PDEs. Okay, so basically the phenomenon in particular that I'm studying is this so-called runaway electron phenomenon. So runaway electrons is something that can happen in high energy plasma, which is exactly what we have in these, tokamak devices. So what can happen is that an electron, or electrons, can be accelerated to relativistic velocities, and that's what we call a runaway electron. And they could actually damage the reactor. So if the reactors are so expensive, in this case, the one I showed was $20 billion, that would be very bad if these runaway electrons could damage this device. So we need to run simulations in order to understand exactly how runaway electrons behave. So the model for understanding these runaway electrons is called the Fokker-Planck equation. So this is a PDE described here. It's a sum of 3 terms. So we have the partial derivative of F, which is the distribution of the electrons, the distribution function of the electrons. So the derivative with respect to time is equal to the sum of these 3 operators: the collision operator, the electric field operator, and the radiation dampening operator. So these operators all have partial derivatives, but I will come back to talking about these in more detail. So the sort of issue is that in order to understand this equation, there isn't a analytic solution to this equation. So in order to understand how solutions to this equation behave, we have to numerically approximate the solutions using numerical methods. So this sort of general idea is that we replace these sort of spatial operators, we discretize them as matrices. So for example, we want to replace this second derivative with respect to x as a matrix. So how we do that, I'm going to talk about this sparse grid DG method. I'm going to start by introducing this sparse grid DG finite element space. So starting with this one-dimensional case, we define this level n nested partition of this interval 0, 1 as follows. So essentially we subdivide this interval 0, 1 into 2 to the n even parts, and we call that the one-dimensional level n nested partition of this interval. And so we then can define the level n degree k finite element space as this piecewise polynomial space, where we have a piecewise polynomial on each of these partitions, and this is we end up getting a vector space out of this that we call the we have polynomials up to degree k. And so this is the level n degree k finite element space. So this is a vector space. This VNK is a vector space of dimension k plus 1 times 2 to the n. So one property of this vector space is that this vkn minus 1 is contained in vkn. So in other words, if we have 2 to the n minus 1 partitions, that's a subset of 2 to the n partitions. So that's how we sort of get this inclusion. So we define the multi-wavelet space as the orthogonal complement of this space Vn minus 1 in this larger space Vnk. So that is how we define this multi-wavelet space. And the reason why we do that is because we get this inductive sort of formula for this Vnk as the direct sum of multi-wavelet spaces. So we can choose a basis for this multi-wavelet space. We choose a specific basis so that we can represent these integral operators as sparse matrices. So the particular basis that we choose is the so-called multi-wavelet basis, defined in this reference, but I'm not going to talk about specifically the construction of this basis, but this is what it's called, as the multi-wavelet basis. And the reason why we choose it is because in this basis, these differential operators can be represented as sparse matrices. So that was the construction for the one-dimensional case. In order to construct the DG finite element space in higher dimensions, we use this sort of tensor product construction. So we let this, we have this notation here, WLK is the multi-wavelet space in this variable XM. So we have D dimensions total. So M is between 1 and D. And then we define this multi-index here of, just a set of indices. And we let this bold WLK be the tensor product of WL1K through WLDK. And so we define the level n degree k finite element space in dimension D as the direct sum of these bold WLK multi-wavelet spaces with where we want the multi-index to have L1 norm less than some fixed n. So this is how we define the multi-wavelet, or the DG finite element space in higher dimensions. So the reason why this construction is nice is because the number of degrees of freedom of this multi-wavelet space, or this DG finite element space, scales as log of the mesh size. So Hn is this the mesh size in one spatial direction. So the number of degrees of freedom scales as log of the mesh size in the dimensions. So if we did a full grid construction, whereas if we just split the spatial domain into 2 to the n partitions in each spatial direction, then this the number of degrees of freedom for that would scale exponentially with the mesh size. But this is exponential of the log of the mesh size. So it's this is a nice construction. And we can see here, this is an example. So it's in dimension 2, the space V3K is the direct sum of these sort of the upper triangular region of these regions. So yeah, this is an example of you can see this sort of indexes. I'm not sure if you can see that, but this is the multi-index, so W30, W21, W12, W03. So each of these has L1 norm less than 3. So this is sort of the sort of picture of the construction. So that was how we discretize the spatial domain. And now I'm going to talk about how we can discretize the this sort of time domain. So so let's assume we've already discretized the spatial domain. So we have this essentially matrix, which is a discretization of the this sort of spatial operator. Then this first example of how we can discretize the time domain is with this forward Euler method. So this forward Euler method gives us an inductive method of determining the value of our function at the nth time step. So essentially, we divide our time domain into n pieces of such that each piece is of size delta t. So the first thing we can do is we can try to essentially discretize this differential operator as a finite difference between the value of the derivative at the next time, or the value of the function at the next time step minus the value of the function at this time step divided by the size of our time step. And then this is called the forward Euler method. And this has the explicit solution. We can explicitly solve for the value of f at the next time step with this formula here. This is called the forward Euler method. So this sort of stability of the forward Euler method depends on the eigenvalues of our matrix A. Which is our spatial discretization. So essentially the property that we want A to have is that we want for all the eigenvalues, if we sort of assume that f is an eigenvalue of A, then we get this sort of formula here where lambda is an eigenvalue, or if f is an eigenvector of A, we get this formula here where lambda is an eigenvalue of A. And what we want in order for, if we iterate this sort of equation, if we iterate this, we don't want this delta t lambda plus 1 to blow up. So what we want is this delta t lambda plus 1 to be of size, the absolute value of this to be less than or equal to 1 for any eigenvalue of our matrix. So this will prevent sort of this unstable behavior. So another way of writing this is lambda can in general be, our eigenvalues can be complex. So we want, essentially what we want is we want to choose delta d small enough so that we can scale all of our eigenvalues down into this circle here, where this circle is the set of complex numbers of such that the magnitude of that complex number plus 1 is less than 1. So in particular, for the spatial derivatives that we're dealing with, the operator should always have a negative real part for their eigenvalues. So we just need to choose delta t such that we can scale all the eigenvalues down into this circle. So we can reformulate this sort of inequality here, this delta t lambda plus 1 less than or equal to 1. We can reformulate this as what we want to choose delta t small enough such that the minimum over all eigenvalues of A is less than or equal to 2 times the real part of our eigenvalue over the magnitude of the eigenvalue squared. And so this is sort of the restriction of the forward Euler method, is that we need to choose delta t to be this small. And so that's why we call this forward Euler method conditionally stable, so that there's this, what that means, the conditionally stable, what that means is that there's this critical time step size such that any larger time step will result in numerical instability. So for example, with PDEs, with second order spatial derivative, this critical time step scales as on the order of hn squared. So hn is the mesh size in one spatial direction. So here's an example. There's this of sort of putting together this spatial discretization and this time discretization. So let's consider this simple advection equation. So we have this df dt equals -2 df dx minus 2 sine of x. So this is an example of a partial differential equation. So this has, with these certain boundary conditions, so at time 0, we have this initial condition of cosine of x. And at the left, we fix the value of the function to be -1. At the right, we fix the value of the function to be 1. So the analytic solution of this equation is just, the value is just cosine of x at all time. So what we do is we use the sparse grid DG method in this example to discretize this operator -2 ddx as a matrix A. We replace our value of our function f with a vector, and we replace this -2 sine of x with this s, which is what we call our source term. And then what we're left with is this ODE. So that's after using this sparse grid DG method. And then what we can do is we can directly plot all the eigenvalues of our matrix A. So this is, for example, at the level 4 sparse grid DG method of degree at most 2, with polynomial degrees at most 2. And this is the plot of our eigenvalues. And and then what we can do is we scale them down into this circle. But what we need to choose delta t to be at most 2.54 times 10 to the -2. So this is the critical time step that we need to choose delta t such that we can scale all of our eigenvalues down into this circle here, this lambda t plus 1 less than 1, or less than or equal to 1. So, okay, so that was the forward Euler method. For the backward Euler method, so this is sort of similar to the forward Euler method, but we define fn plus 1. Similarly to before, we sort of discretize this time derivative as a finite difference, but we do so in an implicit way, in that this is equal to a times fn plus 1 plus sn plus 1, whereas before, for the forward Euler method, our equation was, we had this same left-hand side, but on the right we had fn plus sn. So we can again solve for fn plus 1, but it gives us this implicit solution. So what we have here is this identity minus delta t a inverse times fn plus delta t sn plus 1. So here we're having to do a matrix inverse compared to the forward Euler method where we only had to do a matrix multiplication. So we can do a similar sort of eigenvalue analysis, similarly to the forward Euler method. In this case, the stability region, whereas the forward Euler method was just a circle, for the backward Euler method, the stability region is the complement of a circle. So all this pink area is the stability region for the backward Euler method. The only region where there's instability is in the circle. And again, since we have the operators we're dealing with all have negative real component for their eigenvalues, the backward Euler method is always stable in this case. So since the backward Euler method is always stable, we call it an unconditionally stable method. So that's the upside for the backward Euler method. So we can essentially choose large time steps, and that will still have the stability. We won't experience sort of numerical instability. But the downside is that we need to compute this sort of matrix inverse, the inverse of this identity minus delta t times a. which may be difficult. So for example, if A is singular, if A is singular and delta T is large, then what we may need to do is it may be very difficult to compute this matrix inverse. We may need to solve this sort of a least squares problem at each time step, which can be computationally expensive, and it's definitely more computationally expensive than the forward-Euler method. Whereas we only need to do a matrix times vector multiplication at each time step. So now let's look at this third time stepping method. So first look at the forward Euler method, then we looked at the backward Euler method. Now we're going to look at this Krylov IIF method, which is sort of what I've been focusing on. So again, we go back to our original equation of this df dt equals a times f plus s, where a is this discretization of this spatial differential operator. So what we can do is we can multiply this matrix exponential e to the minus at to each side, and then we can integrate over this time interval tn to tn plus 1. And then what we get is this, again, we get a formula for fn plus 1 in terms of fn. So we have here fn plus 1 is equal to e to the a delta t fn plus e to the a delta t, and then you have this integral which involves this source term here. So what we can do is we can approximate this, the integral of this nonlinear term, this nonlinear source term, with this second order IIF scheme, and we get this this formula here for the value of fn plus 1 at the n plus first time step as a function of the value of f at our nth time step. And so this is the example of a second order method for evaluating this integral, but we could also use a third order method, which is a bit more complicated. It requires the calculation of an additional matrix exponential, but we could do this to get a higher order of accuracy. So the main computational issue with this method is calculating this matrix exponential. So it's also very difficult to calculate a matrix exponential, similarly to how it's difficult to calculate the inverse of a matrix, which was the problem with the backward Euler method. But we can apply this sort of Krylov subspace approximation to approximate this matrix exponential. So essentially what we do is we use this Arnoldi algorithm, which consists of essentially m, we fix this parameter m, matrix times vector multiplications, and what we are left with is, what we're left with is we get this approximation of this matrix exponential times a vector, which we can compute with m matrix times vector multiplications, and then we need to additionally compute the matrix exponential of a m by m matrix. But the hope is that we can choose m to be small, like much smaller than the size of this original matrix. So for example, if we originally wanted to compute the matrix exponential of, say, a 1000 by 1000 matrix, we'd be able to hopefully approximate this by, say, choosing this parameter m to be, say, 25. Then we can approximate this matrix exponential of this 1000 by 1000 matrix by doing 25 matrix times vector multiplications, which are computationally cheap, and then calculate this matrix exponential of just a 25 by 25 matrix. So calculating the matrix exponential of a 25 by 25 matrix is much easier than calculating the matrix exponential of a 1000 by 1000 matrix. So we would like to use this method in order to approximate this matrix exponential. So what are the pros and cons of this IIF method? So the pros are that we can take large time steps, similar to the backward Euler method of being able to take large time steps. And it also has the potential of being computationally cheap. So essentially, we get the pro of the forward Euler method was that it was computationally cheap. The pro of the backward Euler method was that we could take large time steps. So the hope is with this Krylov IF method, we get the best of both worlds, is that it's both computationally cheap and we can take large time steps. Moreover, so if we have no source term in particular, as this sort of parameter m goes to infinity, the error of this IF method should be limited by the error of the spatial discretization. So whereas on the other hand, the backward Euler method has error of order 1 in time. So that's another pro of the IF method. But there's a con of the IF method, and that is that we must choose this parameter m correctly. And that if we choose m to be too small, then our matrix exponential approximation may not be accurate enough, and that we won't get accurate solutions to our PDE. If we choose m to be too large, then this IF method would be too computationally expensive. So, so there's sort of we want to choose m correctly to get both this computational cheapness and this accuracy. So now I'm going to talk about the Fokker-Planck equation itself. So I talked about this sort of spatial discretization. Then I talked about this sort of time discretization. Now I'm going to go back to this model of this fusion energy, which is what I started talking about at the beginning with this Fokker-Planck equation. So the Fokker-Planck equation takes this form. Again, it's this our function is the distribution function of our electrons. And what we have is that the derivative of f with respect to t is equal to the sum of these three operators: this collision operator, this electric field operator, and this radiation dampening operator. So we use a particular coordinate system based on this sort of spherical coordinates, but instead we use this variable Cassi, as we set this Cassi equals to cosine theta. So we use our radial coordinate, our sort of pitch angle coordinate, and then our Cassi, which is cosine of our azimuthal angle. This is one particular example of the Fokker-Planck equation that, in particular, this one describes the pitch angle dependence on f. So this is a one-dimensional PDE, but it's still, you can see that this is still the sum of these three operators: this electric field operation, this collision operator, and this radiation dampening operator. And so this PDE, even though this is only one-dimensional, it's still can be quite complicated. Where this E, C, and R are just constants. And so we also see that we have this is a first order term, as this E is a first order derivative, C is a second order derivative, and in R we have another first order derivative. So let's consider the example of when just the electric field operator, or the electric field term. So let's say that C and R are 0. Then what we have is that just this sort of much more simple equation. So in this case, we have an analytic solution of this equation given here. So it's the analytic solution of this equation is 1 minus phi squared t over 1 minus Cassi squared, where we define this phi as the hyperbolic tangent of the inverse hyperbolic tangent of Cassi minus t. So we're going to use this as a test case to test our Krylov IF method compared to, say, the backward Euler method. So this is example what the analytic solution looks like as t goes to infinity. So you can see if our initial condition is this blue line, so we have say this evenly distributed electrons, then as time goes to infinity, our electrons sort of approach this y-axis at x equals 1 into this sort of delta function here. So this is sort of the behavior of our solution as time goes to infinity. So this is some numerical results for comparing this IF method to this backward Euler method. So what in particular you can see that first of all, we're taking large time steps here. So I mentioned before that for the backward Euler method, or for the forward Euler method, we need to choose delta t to be proportional to the mesh size squared. But here we're choosing delta t to be equal to just the mesh size. So we're taking large time steps, large enough such that the forward Euler method would experience numerical instability. So what we're doing is we're comparing the Krylov IF method to the backward Euler method. So you can see here this sort of computational time of the IF method compared to the backward Euler method. So what I did is I numerically did some numerical experiments to decide how we should choose our parameter m. So we can see that we don't need to choose it very large. We can choose it between 3 and 8, and that the computational time, this is 2.9 seconds for the Krylov IF method. For example, for this level 8 DG sparse grid of polynomials of degree at most 3, the Krylov IF method took 2.9 seconds to compute, whereas the backward Euler method took almost 20 seconds to compute, whereas the error actually is smaller even for the Krylov IF method. So so we can see some benefits for using the Krylov IF method with this table. So let's look at another example of this Fokker-Planck equation. So this form of the Fokker-Planck equation gives the momentum dependence. So before we had the pitch angle dependence on F, now we have the momentum dependence on F. So here again, we have these three operators: this collision operator, this electric field operator, and this radiation dampening operator. This is it looks even more complicated than the pitch angle equation. And here again, we have this is our second order. I suppose collision term is the second order differential operator. This electric field term is a first order differential operator, and this radiation dampening is another first order differential operator. So in this case, this time let's look at the collision term here. So let's set E and R equal to 0. So we have this, even though it's, we're doing a lot of simplifications, but it still looks quite complicated, where we essentially rescale and obtain this PDE here, 1 over p squared d dp, p squared times this psi of p over p df dp plus 2 psi of p f, where the psi of p is this error function. And we have these boundary conditions. But so in this case, we don't know what the analytic solution is, but we do know what the steady state solution is. So we have this steady state solution here, which is this exponential of p squared divided by 4 times a constant. And so this is essentially what the numerical solutions look like. So we can see this blue line here is the essentially the initial condition. We can see that as time goes on, we approach our steady state solution here, which is this dotted line at the top. So again, we're comparing this IF method to this backward Euler method. And for this case, again, we don't need to choose M to be very large. We can choose M to be between 4 and 12. And again, this IF method takes a shorter amount of time. So for example, for level 7 degree of level 7 DG sparse grid and of polynomials of degree at most 2, it took 10 or 100 seconds to compute this Krylov IF method, whereas for the backward Euler method, it took 300 seconds. whereas the errors are again of the same order. And again, we're taking large time steps here. So we're taking the time step delta t equal to the mesh size. And our end time is also very large. So our end time we're choosing to be 260. So yeah, so we can see again that we have some improvements we have some advantage for using this Krylov IF method when compared to the backrow method. Okay, so that's all I have for my presentation. Thank you.
Okay, thank you, Kenneth. Any questions?
Can I ask one?
Yes.
So how difficult a job is this to choose an appropriate M for reasonable speed?
Well, it really depends on, well, to actually choose M, there's different ways of doing it. So first, essentially, let me go back to here. So essentially, oftentimes what happens is that the error between this matrix exponential approximation and the sort of exact matrix exponential, what it'll often look like is the error will be large, and then it'll be, so as we increase M, the error will be large, but then we'll hit this sort of critical M where the error will go down, and then we won't get much more improvement from increasing M. So around this time where around this choice of M where this time goes down or this error goes down is around where we should choose M. So what I did for actually calculating M in these examples is to just choose, just try different M's until we get an error on the same order essentially as the Becker-Euler method, or close to the Becker-Euler method, or smaller than the Becker-Euler method. But for some cases I haven't showed, like for other examples, we could, for other sort of combinations of the Fokker-Planck equation, M may need to be chosen. M may need to be chosen very large, and also there may be some issues with choosing M. If we don't know the exact solution, or if we don't know the analytical solution, if we don't know a steady state solution, then it can be difficult to figure out which M we should actually choose, because it may not be sure if we're not getting errors too small or errors too big, or if we're taking too long. So yeah, it may be difficult.
Okay, so there is no like guidelines or a way to adaptively choose them on the fly or anything. So there's no automated way. Is that correct?
Yeah. I'm not aware of any way of any sort of formula for choosing M. Okay. Yeah, it sort of depends. M is really this sort of dimension of this Krylov subspace, and right. So how to actually choose that to best approximate this matrix exponential, I'm not aware of any sort of formula for that.
All right, thanks.
And you, Kenneth, this is probably suggests a theoretical study for you to do, how to estimate M, right, for given A matrix.
Yeah. This is something I'm sort of interested in, and yeah, I think this, as far as I'm aware, could be more to study there.
Yeah.
Kenneth, I have a question. Can you go back to page 36? Yeah, so for this problem, actually the requirement for backward Euler's method is just the dt equals to hn, not the hn square.
Oh, I see. Yeah, yeah, maybe I misspoke. I meant oh yeah, for the forward Euler method. Yeah, that's for the forward Euler method. Yeah, I suppose, yeah, because this is a first order derivative. Yeah, I see. Yeah, so yeah, that's right. for the forward Elliott method, we need to choose delta t to be on the same order of hn, not hn squared. But I think actually I did try this with the forward Elliott method, and it still blew up, even though it had to be even though it's on the same order as this for this particular choice. I think for what I did, it was too large of a time step.
Yeah, so from the right column by the backward orders method, you can observe the convergence rate is just first order. So that confirms that your dt is hn. So the convergence rate is limited by your dt. But for the other one, for the momentum variable, if you go back to that page, for this one, the red column, you do not have that restriction. You can observe the convergence rate is just as your degree for your polynomial. So there must be something related with the matrix property.
I see. Yeah.
Okay, so I have another question. So now you separately solve the curl IIF for the pitch angle and the momentum variable. Then for combining these two variables, what will be the difficulties?
So for combining the two variables, well, there might be difficulty in being able to choose. Well, first of all, this will be a 2D example. So the sort of spatial discretization will be, I suppose, more complicated. But it may, I don't suppose, I'm not sure if we know a sort of steady state solution or analytic solution in that case for the 2D. But it also may be that we may need to choose M to be very large in order to get an accurate approximation of this matrix exponential. So yeah, I suppose those could be some difficulties.
Okay, another comment is if you just check about the 1D test, it's not the sparse grid, it's just the DG. Okay.
Yeah.
For when we calculate D bigger than 2 or equals to 2, the sparse property will get some reduction for the DUF. But for 1D, there's no reduction for that.
Oh, I see. Okay, that makes sense.
Yeah. Any questions? Any other questions?
Just very quick questions. So all the examples you have showed, they are linear equations, right?
Yes.
Actually, have you ever tried any case associated with nonlinear terms?
Let me correct you. Show the momentum case. It's not linear.
Well,
right.
Let's see. So this is the momentum case. Oh yeah. Well, I mean, I would think that there's no source term here, though, right? For the momentum.
I don't see the nonlinearity here.
Yeah. So Dr. Yuan Liu called this one semi-linear. I'm not sure how to define the semi-linear here.
Semi-linear. I mean, if you have something involves the f as the coefficient of the derivative of f, right? I mean, not the highest derivative, but say here involves second order derivative of f. But if you have something related to f as a coefficient for the first order derivative of f, and then that leads to a semi-linear. But I don't see any nonlinearity.
Well,
I don't know. Each term looks like
in the P, right?
P is a variable, right?
It's variable.
Yeah, it's a variable.
Yes. So yeah, I think for the cases that I was looking at, let me go back to this. Yeah. So this is it doesn't have this sort of source nonlinear term. When I was first starting out, I was doing some examples with the nonlinear term with, for example, diffusion equations, and that when the nonlinear term is where we need this sort of we need to approximate this sort of integral if we have this source term, we need to do this integral approximation of this, say, second order IF scheme or this third order IF scheme. And it seems like it worked pretty well for the test examples that I've done for the diffusion, these diffusion equations. For this Fokker-Planck equation, I haven't tried it yet with a source term, but there are more general forms for this Fokker-Planck equation that do have this nonlinear term.
Here, the S is function of f, is a nonlinear function of f, or just a function of x? Is it the g? You use the p. Sorry.
P.
Or you mean in general, whatever the S is, S can be a nonlinear term. This approach also works.
Yes. Yes.
Okay. Okay. Thank you.
Okay, other questions? Other questions? Okay, if there's no more questions, I'll stop here. Then later I'll post the Kenny's talk to ELC. If you are interested, you can check about that later. Okay, thank you. Thank you, everyone. See you next week. Oh, next week we will have our first external speaker. She is a assistant professor from UMass Dartmouth and talk about the kinetic equation. Okay, see you, everyone. See you next week. Bye-bye.
Thank you.
Bye.